Hello, Calculus 2 students. Just wanted to go through some of the assessment practice problems, beginning with number 1. We have to evaluate this integral. It's going to be theta squared cosine 2 theta d theta. I'm going to attach this practice problem set to the Moodle course page as well. If you lose your hard copy, you can go there to get this as well. So U substitution won't work here. It kind of looks like it might because, you know, if we choose U to be theta squared, then the du, the d theta would be du over 2 theta, which might seem like it's going to cancel out the 2 theta here, which would be nice, but it won't because the 2 theta is part of the cosine, and so you can't just cancel out 2 theta. It would have to cancel out the entire cosine 2 theta, which would not happen. So now I'm thinking, okay, the only thing I can think of is U substitution. Sorry, I didn't mean to say U substitution. I meant to say integration by parts. If I let U be theta squared, and I'm going to let dv be cosine 2 theta d theta. So now du d theta is 2 theta. So du is 2 theta d theta. Okay, so I've got my u, I've got my du. Now let me work on I've got my dv, I need my v. So it means I got to integrate or anti-derive this to get v. So if I want to anti-derive cosine 2 theta d theta, I'm going to think I need to use a U substitution even here. So U substitution with U being 2 theta. So du d theta is 2. So du over 2 is d theta. So that this then becomes the integral of cosine of u du over 2. But instead of putting over 2, I'm just going to put 1/2 out here. So now the integral of cosine of u is sine of u, and u being 2 theta. So my v is 1/2 sine 2 theta. I'm going to go ahead and erase all this that I just did, just because I'm going to need room and I'm going to need an orderly sheet to do this, an orderly way to do this. So I'm just also going to erase this because that's not necessary. Du equals 2 theta d theta. Okay, I'm going to have to keep myself very organized on this problem because it involves a lot. So now the formula is for integration by parts is u v minus the integral of v du. So if I apply that formula, it'll be theta squared times 1/2. Well, I'm going to put the 1/2 in front. Sine 2 theta minus the integral of 1/2. I'm going to put the 1/2 out front again. Sine 2 theta du, which is going to be 2 theta. I'm going to put that right here. I guess, yeah, let me put that right here. Du is 2 theta d theta. I'm going to put the 2 theta right here. D theta. Just because that's how I want to look at it. Now, this 2 can also come out front, but then when it does, it cancels out that 1/2. So let me just go ahead and erase that. So the 2 cancels out the 1/2, so now it's just minus the integral of theta sine 2 theta d theta. Okay, now this is why this problem is so hard, because now I've got another integral that is also, in my estimation, going to require integration by parts again. So, okay, let me take this and integrate it by parts over here, okay? So u is equal to theta. So du d theta is equal to 1. And so du equal over 1 equals d theta, or du equals d theta. Okay, so I'm just going to rewrite that more compactly. Du equals d theta. V is going to be sine 2 theta d theta. And using a similar U substitution to find the antiderivative of this, with u being 2 theta, what I would find is, sorry, that's not v, that's dv. Sorry about that. I would find that v is equal to negative 1/2 cosine 2 theta. Okay, I'm just going to skip a little bit of that work because it's similar work to what we've already shown. You're just taking the antiderivative of sine of 2 theta. To do that, you're going to use U substitution, with u being 2 theta. So now, again, doing this formula, the uv minus the integral of v du, that would then give me that what's in this box becomes theta times negative 1/2 cosine 2 theta, so negative 1/2 cosine 2 theta minus the integral of v du. So that's negative 1/2. I'm going to put that out front. Negative 1/2 cosine 2 theta times du, and du is just d theta. There's nothing else to that. So now this integral, I'm going to go ahead and change this to a plus. Minus negative 1/2. I'm just going to go ahead and write that as a plus. So the integral here is going to be, we've actually already done that integral earlier up here. The integral of cosine 2 theta is 1/2 sine 2 theta. So this is 1/2 sine 2 theta, which, as you can see, is 1/4 sine 2 theta. So this is 1/4 sine 2 theta. Okay, let me see if I can write all this the way I should write it. This is going to be 1/2 theta squared sine 2 theta minus negative 1/2, so it's going to be plus 1/2 theta cosine 2 theta minus 1/4 sine 2 theta. See this negative sign right here applied to all of that. That's why it became a plus 1/2 and why it became minus 1/4. And now that is going to be, that is the full antiderivative that I now need to evaluate from 0 to 2 pi. So I'm going to have to plug in 2 pi to all the thetas, and I'm going to have to plug in 0 to all the thetas, and try to get the numerical answer. So, wish me luck. Here we go. That's going to be 1/2. Why did I put 2 theta? It's not 2 theta, it's pi over 2. Why in the world did I put 2 theta? Glad I saw that. 0 to pi over 2. What did I put? Anyway, it's from 0 to pi over 2. So 1/2 times pi over 2 squared sine of 2 times pi over 2 is just pi, plus 1/2 times pi over 2 times cosine, again 2 times pi over 2 is just pi, minus 1/4 sine of, again, 2 times pi over 2 is just pi. Okay, so all that minus 1/2 times 0 squared sine of 0, 2 times 0 is 0, plus 1/2 times 0 cosine of 2 times 0 is 0, minus 1/4 sine of 2 times 0 is 0. Now this term goes to 0, this term goes to 0. So let's see what we got. So what about this term? Sine of pi. Sine of pi is also 0, so this term goes to 0. Which means this term also goes to 0. Alright, now let's look at this term. That's going to be pi over 4 cosine of pi, which is negative 1. So it's negative pi over 4. And over here, sine of 0 is also 0. So that term goes to 0 as well. So I think my final answer is just going to be negative pi over 4. If I did it all right. I hope I did. Maybe if you find an error in my work, send me a text about it. Alright, on to the next problem. Alright, problem 2. What is true about this series? As far as convergence and divergence is concerned, if I'm doing this series, I'm thinking to myself, these two terms won't matter a bit, and this becomes n squared over n squared, and even the n squared over n squared reduces to 1. So you've got this whole series of from n equaling 1 to infinity of just 1, which means it's going to be 1 plus 1 plus 1 plus 1 for infinity. So you know that's going to diverge. Now, what's the reason for the divergence? What can we give as a good reason? What we're doing here is actually we're doing the limit as n goes to infinity of this sequence that makes the series. And if as n goes to infinity, that's where we get the 1 from. So that is choice D. That's the divergence test. If the sequence itself does not go to 0 as n goes to infinity, that's automatic divergence. That's the test for divergence. So that's good enough for that one, I think. It's possible you could also choose choice B here. That may also be true if you think of this as a geometric series, because the ratio between all these numbers is always the same. It's always 1. So you could say the ratio is 1. Its divergence to being a geometric series are equaling 1. That's maybe also kind of a valid answer as well. Let's go on to the next problem. All right, for this problem, the best thing that I could do to do this usually is to try to get a feel of what's going on by drawing a picture. I've got the volume of a solid which lies between the planes perpendicular to the x-axis at -1 and 1. So think of I've got planes running right here, okay? And also at the +1. So it's anything between those planes. Where cross sections perpendicular to the x-axis between these planes are squares with edges that run between the edges of this circle. And I know that circle looks like this, where this top half of the circle is y equals the square root of 1 minus x squared, and this one is y equals negative square root of 1 minus x squared. So if I've got a square that runs between these two edges of the circle, I can figure out the length of that edge of the square by taking the difference between that top semicircle and this bottom semicircle. So the square edge is equal to the square root of 1 minus x squared minus the negative square root of 1 minus x squared, which is 2. If we change it to plus 2 square root of 1 minus x squared. So then the square area would be the square of the length of the edge. So it's the square of that, which is 4 times, and then that squared exponents cancels out that square root, so it's just 1 minus x squared, which is 4 minus 4x squared. That's the area. Now I want volume. So if I want the volume created by this thing, I get the feeling that this is a cube inscribed inside of a sphere. But anyway, it's kind of hard to imagine that. But I do know that this, imagine that I have this square right here, okay? And the area of that square is now going all the way down this length. So if I integrate that area expression over this whole length here, that will finally give me volume. So the volume equals the integral of the area, 4 minus 4x squared, as we integrate from -1 to 1. I'm tempted to not finish this problem because I know you know how to do an integral like that. Yeah, so I'm going to leave it at that, and I know you can finish that yourself. All right, number 4. Which series converges? Okay. When I'm looking at this, I would like to see, do I automatically know if any of these converge? Are any of these like easy to figure out? So like, you know, are any of these basic? Basic meaning, are they a geometric series or a P series?
You tell me that was geometric. I mean,
And so none of these fit that. C though looks almost basic. Like if we could manipulate that a little bit and think about it, I think we could turn it into something that would be somewhat basic. So I'm going to try that first. So if we have n squared over n cubed plus 4, let's just say as the limit of that thing as n goes to infinity, what's it going to behave like? Well, the 4 won't matter, and the n squared over n cubed becomes what? Becomes 1 over n. And we know that 1 over n, which we might call the P series with P equal to 1, right, this is n to the first, only converges when P is greater than 1. You might also remember that this is the harmonic series, which is fascinating in its divergence. So we know that this one does not converge because of all that. We might even call that the limit comparison test. So it's not going to be C. All right, the rest of these appear to be in the weird category. And remember, the weird category, we are going to use either the integral test or the ratio test. For part A, that to me just looks like it's begging to use the integral test. Why is that? I'm not real sure how to explain why that it appears that way to me. I guess because what makes me think I need to use a ratio test is if I encountered factorials and exponentials and powers kind of all together. And that's not the case here. It's a kind of a transcendental function with the ln. So makes me think integral tests would be a good thing to try. When I'm looking at this integral, I am thinking, by the way, I just rewrote this ln over n as 1 over n times the ln of n. The reason I wrote it that way is because it looks good to do U substitution. Because if I let u be ln of n, the derivative of that is 1 over n, which will then be able to cancel out that 1 over n. Du dn is 1 over n. So now du times n, or I'm just going to put n du, equals dn. So that substitutes in right there. So this becomes the integral of 1 over n times u, because u was ln of n, and then dn becomes n du. And the n cancels there and there, which then becomes just the integral of u du, which you know to be u squared over 2. And u, let me put ln of n back in for u, so this becomes ln of n squared. I'm going to put a 1/2 out in front of that. And I'm integrating that from 2 to infinity because of the limits given here in part A. So let me substitute those numbers in. So it's 1/2 times ln of infinity squared minus ln of 2 squared. But what is ln of infinity? If you remember what a log function looks like, it looks like that. So as n, or as x goes to infinity, or as in the case here n goes to infinity, the function itself is going to infinity as well. Though it's going more and more slowly, it's still going there. So that ln of infinity is infinity, which makes that whole term become infinity, which now dominates everything, so that this is going to go to infinity. So if the integral goes to infinity, meaning it diverges, then the series also diverges. So it's not A. Now looking at B, it's in the weird category. I'm thinking I'm probably going to use the ratio test when factorials and powers or exponentials are all involved. So let me try the ratio test on that one. Remember, the ratio test is A of n plus 1 over A of n, and we compare that to 1. If it's less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, it is inconclusive. So that, in this case, that's going to be n plus 1 minus 2 factorial over n plus 1 minus 2 squared. And I'm just going to go ahead and, this right here is A sub n plus 1. And then I'm dividing by A sub n. But instead of dividing by A sub n, I'm just going to multiply the reciprocal of A sub n. And A sub n would be, I'm just going to go ahead and flip it. It's going to be n minus 2 factorial over, oh, I forgot, I'm flipping it. So this is n minus 2 squared over n minus 2 factorial. And this whole thing right here is the reciprocal of A sub n. All right, now let me do some simplifying. N plus 1 minus 2, that's just n minus 1 factorial. And I'm going to go ahead and put the n minus 2 factorial under that. I'm just rearranging things a little bit. The n minus 2 factorial can come under here. That's fine. And then this is going to be n minus 2 squared over n plus 1 minus 2 is n minus 1 squared. Alright, now let's see what we can do to simplify this. N minus 1 factorial. I would like for that to cancel something on the n minus 2 factorial. N minus 1 factorial is the same thing as n minus 1 times n minus 2 times n minus 3 dot dot dot. Well, n minus 2 times n minus 3 dot 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 is the same thing as n minus 2 factorial. So I can rewrite n minus 1 factorial as n minus 1 times n minus 2 factorial. And the n minus 2 factorial cancels with that n minus 2 factorial, and we're just left with n minus 1 on top right there. So that's n minus 1 times n minus 2 squared over n minus 1 squared. And that n minus 1 can cancel with that n minus 1 squared, and it reduces to this, n minus 2 squared over n minus 1. Which, if we were to expand this out some, it would be n squared blah 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 over n minus 1. And we can see that that in this case the higher exponent is on top. So when the n gets big, this is definitely not less than 1. This is going to go to infinity. This is definitely greater than 1. Mm-hmm. So therefore it does not converge. So it's not B. So I bet it's D. But we just want to make sure because we are that kind of people. Alright. Let's do D and see if we learn something. Again, ratio test. 2 n plus 1 to the 4th over 4 to the n plus 1 times, reciprocating this, 4 to the n over 2 n to the 4th. What did I say? Did I say the integral test?
I hope you said the ratio test.
I meant to say the ratio test. I got my dad sitting here by me. He's fascinated by what we're doing. And who wouldn't be? Okay. So he's helping me think through these things too. It helps to have somebody that speaks your language sitting here thinking with you. Alright, so this and this can reduce each other. They're like bases, so we can just subtract their exponents. We get 4 to the negative 1. If we say n minus n plus 1, that becomes negative 1. So it's 4 to the negative 1, which is just 1 over 4. And if we do this over this, that's going to be times, that's going to be 2. You know, if I expand this thing, it's going to be n to the 4th, yada, yada, yada. And then that 2 is going to multiply and become a 2n to the 4th at some point. Now, those other terms just won't matter much as far as this ratio test is concerned, as far as limits as n goes to infinity are concerned. And this factor down here is 2n to the 4th. Now, I'm also, that 1/4 is going to play a major role now, because that's now going to become, if I multiply the 1/4 by this thing, it's just 2n to the 4th, blah, 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 over 8n to the 4th. And now, the degrees are the same. So if n gets big, it's going to go toward the ratio of the leading coefficients. This is going to go toward 2/8, which is less than 1. Therefore, convergence. Yay. Party time. D is the answer. Okay, that's number 4. All right, we're going to try to do 5, 6, and 7 right here. Okay, number 5. That's looking like one of these special integrals, like transcendental function kind of thing, like a trig function integral. And I'm looking on my derivative and integral sheet, which you have. And I'm looking at number 18 on the integral formulas. Number 18 on the integral formulas looks like this. It says the integral of du over square root of a squared minus u squared is equal to arc sine of u over a plus c. So that looks like it would fit this situation right here. Just the dx could be on top or the dx could be out to the side. It doesn't really matter. So if I apply that formula to this, I would say then this integral is going to be equal to the arc sine. Here a would be 4. So it's the arc sine of x over 4. And since it's a definite integral, I have no plus c. So that's from 0 to 3 halves. So that's going to be arc sine of 3
0
x over 8. 3 halves. 3 halves goes, sorry, 3 halves goes in for x. 3 halves over 4. What's 3 halves over 4? That's going to be 3/8, isn't it? 3/8. Ooh, that ain't good there. Minus arc sine of 0 over 4 is 0. So arc sine of 3/8. I'm trying to think, what is the angle that has a sine of 3/8? And probably, I kind of tried to make up a problem here, and 3/8 didn't really fit in very well, because it's not one of our known angles. Of course, we could do it in our calculator and get the arc sine of 3/8 as an approximation. Let me go over here and do arc sine of 0 real quick. The angle whose sine is 0 would be 0 or pi, but let's just say 0.
What's got to be between negative pi over 2 and pi over 2?
Right. If you limit the domain to that, then it would be 0. So then we could just say the answer is arc sine of 3/8. And that would be an exact way to write the answer, or we could get a decimal approximation in our calculator. All right, that's good enough for number 5.
If it was square root of 3 over 2, it would be like pi over 3 or something.
Right. Okay. Number 6. Number 6. U substitution seems like a good idea, because if we let u be 1 minus r to the 4th, then part of that derivative is going to be an r cubed is going to be in there that would probably cancel this r cubed on top. That's the theory we're going in with, so let's try that. If we let u equal 1 minus r to the 4th, then du dr equals negative 4r cubed, and so du over negative 4r cubed equals dr. So that then this integral becomes 16r cubed over u, and then dr becomes du over negative 4r cubed. But I'm just going to put an r cubed right here. Well, I guess I could put a negative 4 also, because that also will reduce that 16. So the r cubes cancel. That's nice. The negative 4 can cancel and make this 16 become a negative 4. So now I can simplify this integral to negative 4 integral of 1 over u du. And the integral of 1 over u is one of our special integrals. Look on your integral sheet, and it is ln of u. So this then becomes negative 4 ln u, where now I substitute back in for u, and it becomes negative 4 ln of 1 minus r to the 4th plus c. Because it's an indefinite integral, that makes it have to put plus C, and then it's done. You don't have to plug in any numbers. You're done. Number 7 is a doozy. We did not cover what you need to do number 7, so I'm going to do it right now. It's using a technique called integration by partial fractions. Kind of like integration by parts and integration by trig substitution. This is just kind of a neat technique, a neat little way to do things. It's pulling a trick out of your hat to be able to integrate this thing. By the way, I changed this number 7 from what you have on your hard copy because I tried to make up a problem that was similar to a problem like on your assessment, but in doing so, I made up a problem that was not possible to do with integration by partial fractions. So I changed it. So just don't worry about the problem that's on your hard copy. Okay. Let's see if I can figure out how to do this by partial fractions myself. What we want to do is we want to change this to, we want to separate it into different fractions. Make it into different fractions. So first we're going to rewrite it in factored format on the bottom. If we could factor out an x, then that becomes x squared minus 3x plus 2. And then that would factor as x minus 2, x minus 1. And what you do is you say that's equal to a over x plus b over x minus 2 plus c over x minus 1. Some kind of way there's an a and a b and a c that will make these become all separate. And now the way that you do it is you're going to say, well, I'm going to multiply everything by this whole denominator. Every term is going to get multiplied by that whole denominator right there. And when you do that, obviously the left side of this equation, the denominator is going to cancel out when I multiply by that denominator. It just becomes 1. And then this term is going to get multiplied by that whole denominator. The x is going to cancel that x. That x will cancel that x. But the x minus 2 and the x minus 1 will not cancel. So you now have a times x minus 2 times x minus 1 plus with b, the x minus 2 will cancel with that x minus 2, but you'll be left with the x and the x minus 1. So it's going to be b times x minus 1. Plus, in this fraction, the x minus 1 will cancel with that x minus 1, but I'm still left with the x and the x minus 2. So c times x minus 2. Okay, we're trying to figure out what our a, b, and c are. So what we do is we're going to substitute in strategic values of x that will help us to get a, b, and c. The first thing I'm going to substitute in for x, I would like to substitute something in for x that would make this term become 0. So 2 would work, or 1 would work, because it would make one of these factors become 0. I'm just going to put in 2. Let's say x equals 2. If I let x be 2, here's my work. If I let x be 2, then I will have 1 equals, the whole first term will become 0. So it equals 0 plus b times 2 minus 1 is 1 plus, if I let x be 2, then that 2 minus 2 also becomes 0 over here. So the whole c term becomes 0, so it equals 0. So then 1 equals 2b, so b equals what? a half. We found b. b is a half. Let's do it again to see if we can find another letter. Now maybe I want the b to cancel out. If I want the b term to cancel out, maybe I should let x be 0, or maybe I should let x be 1. I'm going to let x be 0. So if I do that, I get 1 equals a times -2 times -1 plus this whole term becomes 0 plus this whole term also becomes 0. So now I get 1 equals 2a. So that a is also happens to be 1/2, coincidentally in this case. Lastly, I will want the, what did I just make cancel out? I made the a term cancel out.
Okay, then you made the b.
Alright, now let me let x be 1. If x is 1, I already did x is 2 right there. I'm going to let x be 1. So if x is 1, what do we get now? 1 equals 0, because the a term canceled out, plus 0, because the b term will also cancel out, plus c times 1, parentheses look like c's, sorry. C times 1 times -1, which would then make 1 equals -c, so that c is then -1. We've now found our a, our b, and our c that would give us an equivalent expression to the original expression. Alright, let's see if we can now work on this integral in a new way. So now this is the integral of 1/2 over x. So in other words, 1 over 2x plus b was also a half, wasn't it? Plus 1/2 over x plus 2, which would be 1 over 2x minus 2. I said x plus 2, I meant x minus 2. Plus, if c is -1, that would be minus 1 over x minus 1. And so now I can evaluate all these terms with their own integral. So I can just integrate them all separately. And let's see what we can do with that. If I factor out a 1/2 here, and that's the integral of just 1 over x, which we know that's going to be ln x, right? The integral of 1 over x
1/2 ln x
is ln x, so 1/2 ln x. Alright, plus, let me factor out a 1/2 here as well. It's the integral of 1 over x minus 2. And if it was, I have a special integral here of 1 over, hold on a second.
It's just ln of x.
One thing I am missing here is absolute value symbols. So plus the integral of this is 1/2 ln of x minus 2, absolute values. Okay, minus integral of 1 over x minus 1 dx. So minus ln absolute value of x minus 1. And this right here, oh yeah, it's an indefinite integral, isn't it? So what do I need to put? Plus c. So all of that should be the integral, the indefinite integral of that pretty complicated integral right there. And what was this called? This was called integrating by partial fractions. A new technique for you. So do the best you can on that. Number 8 really isn't too bad. A little bit of trickiness in it. Find the area bounded in the first quadrant by the curve defined by the following function and the x-axis on the interval 0 to pi. Okay, so in general that means that I am doing an integral of that function, 1 minus sine x cosine x as x goes from 0 to pi dx, because an integral finds area, but an integral finds the signed area. So the little bit of trickiness, it wants the area bounded by that curve, between that curve and the x-axis, whereas an integral finds the signed area, so that if it goes down like that, it will take that area and subtract that area, whereas this wants the total area. So we want to take that area and add that area to it, if that happens on this problem. So we need to figure out if that does happen. So I graphed this problem in the calculator, and it kind of looked something like this, and it kind of flattened out right here and then kept going down. So it is a problem.
Why is the area 0? It should be 0.
So we want to add this area with this area. So in order to do that, we got to find out where that thing crosses. So we want to set that function equal to 0 to figure out where it crosses. And it's already kind of factored out for us. We can just set the two factors equal to 0. And solve it. So if we move the sign over, we get sine x equals 1. Take the arc sine of both sides. And so we're looking for the angle whose sine is 1, which is pi over 2. Here, take the arc cosine of both sides. Looking for the angle whose cosine is 0, and that's also pi over 2. So we actually get pi over 2 with a multiplicity 2, which might make some people think that might mean that the curve hits the x-axis and bounces and goes up. But what it really means is that the curve hits the x-axis in such a way that the derivative is 0. But it could go up, or it could still turn and go down from there. And we looked at the graph of this thing on the calculator, and it actually turns and goes down. So we just figured out where that happens, so that we can just do the integral from 0 to pi over 2 of 1 minus sine x cosine x, and add that with the integral from pi over 2 to pi of 1 minus sine x cosine x. But we need to make sure like if we get a negative answer here, then just take the absolute value and get the absolute value of it. I actually know that the area here is going to come out negative, because that's where it goes down below the x-axis. So I could just take the absolute value and add it, or I could just, since it's going to be negative, I could just subtract it, because subtracting a negative adds. So I'm just going to do that. Another thing you could have done is you could have added it and swapped your limits of integration, and that would have made it come out positive. So all kinds of options there. Now, to actually do this integral, U substitution would work very well. Why I think that is because if I take the derivative of 1 minus sine x, I'm going to have a cosine x in there somewhere that can cancel out. So I'm going to let U be 1 minus sine x. So du dx is going to be, the derivative of 1 is just 0, and the derivative of sine is cosine. So since there's a negative sign in front of it, it's going to be negative cosine x, so that du over negative cosine x equals dx. Now, so that means that this integral is going to become the integral from 0 to pi over 2 of u cosine x du over negative cosine x, so that the cosines then cancel. And so then this is going to become the integral from 0 to pi over 2 of u du, and that negative sign that was on that cosine, I'm just going to factor it out front there. This one is the same exact thing, so minus negative integral from pi over 2 to pi of u du. And minus and negative actually makes that become plus, doesn't it? So let's just write it as a plus. And so this makes us then say this is going to be equal to negative u squared over 2. Or I could just say 1/2 u squared plus 1/2 u squared. And what was u? U was 1 minus sine x. Let me substitute that back in. So it's negative 1/2 1 minus sine x. And this is going to go from 0 to pi over 2 plus 1/2. Forgot this is 1 minus sine x squared because it's u squared. 1 minus sine x squared from pi over 2 pi, which is going to equal 1 minus sine pi over 2 squared minus 1 minus sine of 0 squared plus 1/2 1 minus sine pi squared minus 1 minus sine of pi over 2 squared. Which is going to equal 1/2. Alright, sine of pi over 2 is 1, so that's 1 minus 1, so that becomes 0. Sine of 0 is 0, so that's 1 minus 0 squared, so that's 1. So that's going to be negative 1. For that one. So now plus 1/2. What do we have here? Sine of pi is 0, so that's 1 minus 0 squared. That's 1 squared, that's 1. And sine of pi over 2 is 1, so that's 1 minus 1. Well, that's 0, so that whole thing becomes 0, so that's just 1. So this is now going to be 1/2 times negative 1 is 1/2, plus 1/2 times 1 is 1/2, so 1/2 plus 1/2 is 1. The answer is 1. That is the area bounded by that curve and the x-axis. Alright, number 10. This problem is harder than I want it to be. But let's do what we can on it. The volume of the solid generated by revolving the region bounded by the first quadrant and the curve y equals e to the 2x and the line x equals ln3. Okay, let me draw that for you. E to the 2x in the first quadrant would look something like that. And ln3 is just going to be is just going to be a vertical line crossing the x-axis at ln3. And we are revolving this thing about the y-axis. Okay, so if I revolve that about the y-axis, then it's going to come over here to draw its. I'm kind of trying to draw a picture of the situation here. So it's revolving around the y-axis, something like that. Okay. So to me, it would make sense, the most sense, to do this with cylindrical shells. So I'm on. It's like I'm making a cylinder right here. That is going to be a little piece of this great big volume. If I were to take that cylindrical shell, and you remember the cylindrical shell kind of has this small thickness, this dx thickness. So if I unravel the cylinder, then it is a very thin, long rectangle. Okay, and the length of that rectangle is the circumference of that cylinder, which is going to be 2 pi r, where r is this radius right here. It's this radius right here. And what is that? That is the x coordinate of this point, which is just x. So the length is 2 pi x. That's the length of that rectangle. The height of this rectangle is the y coordinate of this thing. That's the height of that cylinder, which is just going to be, the height of this thing is the y coordinate, which is e to the 2x. And the thickness of this thing, or the width, whatever you want to call it, is this just barely getting thing, which is dx. So the whole volume will equal 2 pi x, that's the length, times e to the 2x, that's the height, times dx, that's the width or thickness. And it'll be the integral of all that with respect to dx. So this is, if you get it set up like that, I think that's very good. What I don't like about this problem is that even from here, you now have to do this integral by integration by parts. So it not only tests you on setting up a solid revolution, then you have to actually figure it out by integration by parts. That's I'm not a big fan of putting both of those together in one problem for students. But anyway, so that volume, I'm going to factor out a 2 pi. So it's just the integral of x, e to the 2x, dx. And we're integrating from 0 to here. So from 0 to ln3. 0 to ln3. Alright, if I do integration by parts here, with u equals, where u equals e where u equals x, and dv equals e to the 2x, so that du equals dx, and v is going to be e to the 2x over 2. If you need to integrate this or take the antiderivative of e to the 2x, you might use U substitution to get to that. And anyway, think about taking the derivative of this to get that, and you'll see that that is the case. So that now I have uv minus v, the integral of v du would be, uv would be x times 1/2 e to the 2x. I'm going to put my 1/2, so e, right there, e to the 2x, minus the integral of v, which is 1/2. I'm going to put my 1/2 out there, e to the 2x du, and du is just dx. Okay, now integrate this, and I get the integral of e to the 2x is 1/2 e to the 2x. And I still got that 1/2 out there as well, so that this whole thing is 1/4 e to the 2x. So now I've got 1/2 x e to the 2x minus 1/4 e to the 2x from 0 to ln 3. Okay, so let's plug that in. It's going to be 1/2 ln 3 e to the 2 ln 3 minus 1/4 e to the 2 ln 3 minus 1/2 times 0 e to the 0, which is going to be 0 anyway, minus 1/4 e to the 0. I could do some tricks here if I want to. That could be ln square root 3 if I wanted it to be, because the 1/2, if you use your log properties, could become the exponent on that 3. So 3 to the 1/2 is the square root of 3. And this 2 could become the exponent right there, so it becomes e to the 9th. Let me do this. Let me factor out e. Let me factor out e to the factor out e to the 2 ln 3. Because it's in common. E, so that's going to be e to the 9th. And that's going to be ln square root 3 minus 1/4. And then e to the 0 is 1, so that's minus or plus 1/4. And so then this becomes what? This becomes what just happened. So this becomes e to the 9th ln 3 minus e to the 9th over 4 plus 1/4. I don't know how much else you should do here. I mean, that could be, it could be over even there. I don't really see there's a whole lot of helpful simplifying that can be done there. Yeah, we'll just stop it right there. That's number 10. Alright, number 11. Which of the following statements is true regarding the following infinite series? And we have this series. We have 3n squared plus 5n over 2n cubed plus 5n plus 7. If we do the limit of this thing as n goes to infinity, those terms don't matter anymore, and you have if we have a higher exponent on the bottom,
so it goes to 0.
The sequence goes to 0, but not in a way that converges, because we know, like, just reduce this part. If you know, algebraically it's not right, but as n goes to infinity, it would be fine to do that. If you reduce this part, it becomes 3 halves, and we can even just factor out the 3 halves and think of it as 1 over n. What does 1 over n do as n goes to infinity? The series 1 over n, the harmonic series, diverges. So if we compare this to the harmonic series, it's going to behave like that. So it's also going to diverge, and we would say that it diverges because of the limit comparison test. Simple enough. And we are finishing up with problem 12. This problem actually isn't so bad compared to the rest of these problems, but we just have to find the region that is enclosed by these two parabolas. The region that is enclosed by these two parabolas, and then just do an integral to find that area. But I kind of want to draw a picture of this to see, to look at the region. Y equals x squared, I know what that looks like. Now this one, 2x minus x squared, I don't know exactly what that looks like. I know it's going to open downward. If I factor out an x, that gives me 2 minus x equals 0. So it's going to cross at 0 and at 2. So 0. So it's going to be something like that. So the region will be something along these lines. That's what I want to find. Now I need to know where they cross. I already know they're going to cross right there at 0 since both of them hit there. But where do they cross here? How do I find that? I set them equal to one another and solve. X squared equals 2x minus x squared. I'll go ahead and add the x squared to both sides to combine like terms, and I'll go ahead and subtract 2x from both sides. And I get 2x squared minus 2x equals 0. I will factor out a 2x and get x minus 1 equals 0. Set this equal to 0 and this equal to 0, and I get x equals 0 and 1. So they cross at 0 and they cross at 1. Perfect. I can now do the integral from 0 to 1 of this guy minus this guy. Okay? Or maybe I should say the red one here minus the blue one here. So the red one is this one. This is the red one. This is the blue one. So that's going to be 2x minus x squared minus x squared, which then becomes the integral of 2x minus 2x squared dx. Which is going to be, integrate that, we get 2x squared over 2 minus 2x cubed over 3, which is going to be x squared minus 2/3 x cubed from what to what? From 0 to 1. Plug in my limits of integration. That's going to be it's going to be 1 squared minus 2/3 times 1 cubed minus 0 squared minus 2/3 times 0 cubed Back term is 0. That term is 0. This is just going to be 1 minus 2/3, which is 1/3. The area, that area right there is 1/3 square units.
That's it.
And that covers all the problems. Do the best you can on this exam. Actually, I think there was one problem I didn't cover, and it was number 9. This problem about converging absolutely over what interval. That problem, I'm just not sure about that problem. I will try to learn more about that problem, but at this point, I can't do it. I don't know it yet. So can't help you on it, but just do the best you can on that online assessment. On all the rest of the problems, take a good guess on that problem like that, like number 9, and I certainly won't hold a problem like number 9 against you on the grades, on the ultimate grades in Moodle. So don't worry about that. But yeah, I'll see you in class next time. Good luck.